Thank you so much, and thank you for the opportunity to be part of this amazing event today, or this week. I Indeed, I'm going to now talk about the intersection of computer science, something at the intersection of computer science and game theory, and I guess this is meant to be a setting in which participants strategically interact. Participants here could be machines or could be humans, and wonder about what outcome should we expect. So the main question that I have been considering, maybe the last, at this point, maybe as much as 20 years, is thinking about how much selfishness deteriorates social outcome. And that was dubbed by Christos Papadimitriou in a cutesy term as price of energy. The focus today is actually a little different from the original focus at looking at Nash equilibrium of games. Instead, I want to focus on games where participants interact repeatedly, and the assumption will be that they're trying to learn what might be good for them. And he wonders what happens in that case. And I'll come back to tell you a little bit about why I like this setup, but maybe even to start with, there are lots of interactions where the interaction is indeed repeated. So this is, not a one-time thing, but a repeated setup. So first, a little bit about this price of energy. So, price of energy is how much you lose if people interact selfishly. And what I want to distinguish is something on the bad side that is dubbed the tragedy of the commons, which is an example in which when selfish people interact, and I guess in the story here is that there is this patch of grass on which everyone is allowed to put as many cows as they feel like to graze on the grass. And when they do that, then there will be so many cows that all the cows will be starving. And it completely ruins social welfare. It would be better for society or better for everyone if they limited the number of cows. This can be done with a sort of simple mathematical model to integrate that as the patch gets too crowded with cows, the value for each cow is decreasing so fast that even the total welfare decreases. So this is a tragedy because welfare went down with an arbitrary factor. In contrast, I'm going to, maybe my favorite example, I'm going to think about a couple of games where this isn't happening. My favorite game in life is what's called traffic routing. And traffic you can think of as cars as you're driving home, especially if you live someplace pretty far away, or packets on the internet. The mathematical model is that as traffic increases on a particular segment of the highway, people have to slow down. So, the time at which the text is a monotone increasing function of the congestion on the edge. In that way, it's a game. When I go on a path that's short for me, I'm making it a little bit more congested and hence a little bit slower for everyone else. And that's, a nice example of a repeated strategic interaction. If you drive, that's something that people do a lot. And if it's packet routing, it's even worse. The packets get routed on the internet every millisecond, tons of them. So just to get an example, and this is my sort of example that started me in this area, goes under the name of Brace paradox, both to drive home the point of, selfishness can actually hurt, and also I love this example so much that even if all of you have seen it already, maybe it can't hurt to see it one more time. So in this is a traffic routing example. The example suggests that there are two of these highways that takes an hour to go, but that's the dark black ones. And then through two red paths that somehow very congestion sensitive, and there are X cars on it, it takes X over 100 hours. So with 100 cars, what the natural solution is that they divide 50-50, and each of them take an hour and a half to get to their destination. And this isn't ideal, but it's okay. However, the paradox goes that if an inventor somehow decides that they can make a tunnel and quickly get people across from C to D in 0 seconds, because whatever, so there's magic happening there, then this is no longer what's called a Nash equilibrium to drive this. Namely, people might notice that they can do something better, namely this. On the red dotted path, 50 plus another 50, they can get there in an hour. That's a huge saving. And unfortunately, if every single one of them does this, then it's going to cost them 2 hours to get across, because somehow the congestion now went up to 100 every single place. And what's worse, this is a Nash equilibrium. That is, once you're in this traffic pattern, an individual, there's not much they can do. They can go back to the original path, but it also not takes 2 hours. Everything is 2 hours. So all the participants suffered, and I guess what one thinks about a paradox, and by the way, Braze was a German mathematician, just to drive the point home, who noticed this is Braze paradox. What's paradoxical is that we put in an extra edge, which in normal optimization only makes things better, but I guess because of selfishness, it did actually make it worse. So that's sort of, a starting example. I think the classical view of this was that Braze paradox just says that life is really bad, that putting extra edges can hurt. My very computer science view of this was, it's not so bad. It's only 33% up. That's not so damaging. So I guess I started to work on how bad is this. And I guess now more than 20 years ago, we had this result that said that if you compared the Nash equilibrium to a fully optimized traffic pattern that carries twice as much traffic, so unlike the picture here, it could be traffic going from various points to destinations, but the traffic rate from a pair I is Ri. If I compare it to the cost of a centrally designed optimum that's carries twice as much traffic, we showed that the Nash equilibrium is necessarily cheaper than double the traffic rate. I guess the price of energy definition actually wasn't quite this. This is a bit of a cheat with the double traffic rate. What I should have done is price of energy compared to the worst Nash equilibrium to the social optimum. Here we are kind of doing a dual style comparison. I like that dual style comparison, and maybe we'll tell you more about it, or definitely we'll tell you more about it in this talk. But the message here is that if you choose between centrally arranging traffic, and that's good luck in doing this with cars, telling them which way to go, and equally good luck in telling it with internet packets. Like, that's a very big system. Somehow millisecond by millisecond knowing where to send the packets, good luck. So probably that's not a viable option, but it also says that that's not what you should do. You should increase the capacity. Now, increasing the capacity on highway is also a hard task, but the internet, that is what we're doing. When there's too much congestion, they just increase the pipe. The theorem says that's mathematically the right thing to do. That's what we should do. So what this question asking is, how much extra resources do we need to actually alleviate the harm that selfishness can cause in choosing routes? Okay, so that sort of was, as I said, 20 years ago, and the intervening 20 years, especially the first 10 of them, there were lots and lots of beautiful theorems on other things with Nash equilibrium bounds, versions of this routing game, bandwidth sharing, which are sort of internet-motivated questions, and tons on auctions, which I'm not really going to. First price auction, second price auction, multi-item auctions, all kinds of things. I'm not going to much touch on this, but there is a large literature in beautiful price of energy theorems. What I want to focus on is this learning thing. So there are some problems with the original definition with the Nash equilibrium. So remember, Nash equilibrium was a stable state of affairs where all the players think that what they're doing now, given what everyone else does, is as good as possible for them. They don't have a selfish improvement. They don't have any incentive to deviate. I would categorize troubles in sort of two categories. One is maybe an informational one. Many games have multiple Nash equilibria, so assuming they found this, they had to coordinate among each other. And maybe worse than that, you literally have to know who else is there to know what the Nash equilibrium might be. So, in the driving or packet routing case, you just have to have a global view of the whole system to decide where is that Nash equilibrium. And then there is a second problem that shown by Daskalakis, Goldberg, and Papadimitriou, who actually was awarded a maths prize for this in, I forgot which Congress. The one that was in, sorry, I don't remember where it was. That it's computationally hard to find it. So, even if I had central computers, good luck in finding the solution. So, there are some troubles with Nash equilibrium. And I want to actually instead focus on this learning. So learning is most useful in games such as packet routing, or actually some of the online auctions like the ad auctions that's happening on Google, where each of the interaction is really not much value. So here is the way I want to view it. You repeatedly interact, you do something happens, then you do it again and again, something happens. I assume that people care about the average performance, that is over time how well you're doing on average. But each of the individual actions is so cheap, like in ad auctions, it's usually pennies or maybe a couple dollars. And remember, ad auctions is fueling the whole online economy. So there's a lot of money there. But each of the individual actions is so cheap that trying things and learning from it is very reasonable. The same happens on online packet routing. Like, you run a packet, you lost it, you just resend it, not that big a deal. But if you lose a lot of packets, you're in trouble because then your stream is suffering. So we're going to assume that players will try to learn from past data, and I will ask two questions. This talk I'm going to mostly focus on what can we say about learning outcomes. But I'm also very interested in, and we'll try to end with good questions about what might we mean by learning? Or maybe we'll start and end with the questions of what should we mean from learning with data? What is the good way to learn in situations like this? So that will be the message here. So learning in repeated games has long history. I guess one way to view this, it certainly started before I was born. Two mathematicians, Brown and Robinson at UC Irvine and Berkeley, respectively, both in around 51, started to think about it. Their method of learning was called fictitious play, or is called fictitious play. It's a particular system. You pass response on best history, assuming other people are not learning on you are, which maybe is a bit crazy. Because of this, they were hoping that this is a form of pre-play, that people do this, and then this leads them to Nash equilibrium, and then they can play the Nash equilibrium at the end. This agenda, I would say, didn't work out. So there are a couple of theorems, including Julia Robinson's from the 51 paper, that in some special cases of games, two-person zero-sum games, or very tiny games, two people, only two strategies each games, it does, in fact, what they want, it happens. They find the Nash equilibrium. But generally, the answer is no, they don't. So mostly it's not true. And let me actually tell you what is it that they were hoping, and what is it that's happening instead. And I guess we want to think that what's happening instead is good enough. So Nash equilibrium of a one-shot game, what they were hoping that the pictures suggest is that they start playing, they do all kinds of things, and after a while they approach or reach what was the Nash equilibrium, and then it's stable, they can just repeat it. So this the green A's without any upper index on them, they reach the stable solution. At this point, everyone is happy, and they just repeat it over and over again. What does that mean? That means this equation that you see in the bottom, that the utility, and this is a notation that we have seen the first day also, on one side. I don't know if I can point. Yeah. On this side, you said the utility agent I gets if they play the vector AI, A1 up to AN. And the other side, I said the utility the same agent would get if she or he would change his strategy to some other X, everyone else would pay the same A. So A minus same A, everyone else other than I kept their strategy, person I switched to strategy X. And what this says is that you can't improve your own welfare. Your welfare with the A is as good as it gets. If you switch to something else, it doesn't get any better. That's what, and I guess I'm going to call it no regret, or they don't have regret for what they're playing. And what they hoped is that they're going to reach this sort of no regret state, but that's actually not happening. Weirdly enough, it's not even happening. So first of all, adductions, it's not happening. This is data from a paper I have with two of my co-authors, Denis Nekipalov and Vasilis Sirkanis, where we looked at Microsoft data and wondered about something which I can come back to. But in particular, this is bidders that were bidding in an ad auction. And as you see, especially the red curve and many of the other ones, it's absolutely not stable. People are changing their bids all the time. And I guess I know why. It's because there are these machine learning firms that specialize on helping people bid. They're learning machine learning algorithms. So I think this is what we should model. The learning algorithms that are trying to help people bid. What happens when everyone does this? So again, the model will be is that, again, people repeatedly interact. When they start, maybe they're clueless, but hopefully after a while they figure out what's good for them because they use the learning algorithm to do so. And I guess the Nash equilibrium assumption was that they not regret what they're doing. Here is one learning assumption that is very reachable, which I'm going to think of as a behavioral assumption. The behavioral meaning I'm going to make the assumption that everyone can reach this condition, and here is the condition. It's almost the same as what I had before, that is the utility they get over time is as good as any single strategy with hindsight. So let me try to say this in English in the driving version. Like it could be that when you're driving to, I don't know to where from here, Frankfurt from here, there are multiple highways, and turns out when it's rainy, it's really good to drive this way, but when it's sunny, it's better to drive this other way. Or maybe on Tuesdays, there is bad traffic on one of them. On Wednesdays, there is other kind of traffic. That's very complicated. But if there's a single way that's always good, and you're not noticing it, you're doing something wrong. So a learning algorithm should notice this much. If there's a single strategy X that is always better than what you're doing, or at least on average it's much better than what you're doing, please wake up to this. And what I mean by putting a little error term on it, and this is this little law of t at the end, is that, well, of course, when you started learning, you might have made some mistakes. So with a little bit of error, you should do at least as well as a single strategy with hindsight. And again, you could do better than this, and that's fine with me. You don't have to follow these algorithms. One nice thing about this, there are plenty of algorithms that achieve this. It started actually, an econ community calls this, instead of no regret, they call it Hanan consistent because of the 57 paper of Hanan that suggested an algorithm. I favor personally the other two algorithms that are much more recent from the CS community because those are simpler algorithms, but whatever. There are many algorithms, and in fact pretty simple ones that achieve this, but I'm not going to make the assumption that people run these algorithms because I don't know if they do. In fact, probably they don't. But simply that they achieve this condition, which I think is a very reasonable natural assumption. I'm going to ask the question, what can I say about the outcome if all the players are smart enough to achieve this pretty low bar for what does it mean that you learned? So it turns out this also has been studied, and I guess what they reach and the limit is called course-correlated equilibrium, and has a very Nash equilibrium-like condition. Expected payoff is greater than the expected payoff of any fixed strategy with hindsight. That thing it's written there was literally the condition I named. Except it's almost the same as Nash. I just gave up on the stability. And in fact, even the existing results, the two-person zero-sum game. So here is one favorite, or many people's favorite two-person zero-sum game, rock, paper, scissors, that I wrote on the side up there. I hope everyone knows how many people know what rock, paper, scissors is? Good. Okay, that's what I assumed. So rock, paper, scissors has a unique Nash equilibrium in which everyone's supposed to randomize one-third, one-third, one-third. If they do any sort of learning, and this is true for no regret learning or fictitious play, what they're going to converge to is not that. We'll converge to this 6 cycle that I have up there in red, which is what? It has the right marginal distributions, everyone a third of the time playing each of the strategy. It has the right payoff, everyone on average is getting 0, but it doesn't have the joint distribution. They became correlated. And what happened here is they correlate based on shared history. They're both learning from the history. That's a correlation device, and they actually end up correlating. So this is a two-person zero-sum game where the right values and the right marginal distributions are happening. In other kind of games, even that's not happening. They just become correlated. But they satisfy that inequality on the top there because that was the definition of no-regret learning. So that's what happens when people learn. What's nice about learning, and this is also roughly 10 years old, is that if I take I rewrote here the price of energy definition, so in the utility form, so I compare the utility of a Nash equilibrium compared to a socially designed optimum that's trying to make the utility as high as possible, that in a sequence of papers starting with one with Avrum Blum and his students at the time, they actually suggested this no regret as a behavioral assumption and proved that almost all the results we have, and I guess 90-somewhat% of them, that we have for price of energy automatically extend to no regret learning outcomes. That is, we don't need the stability, we just need the inequality. In fact, we even extended it to a bit more complicated place with dynamically changing population. And at that point, which I guess now more than 10 years ago, the general belief that all of us subscribed to was that no regret is the natural, strong enough assumption. It's a weak assumption, you can do better than that. But as long as everyone does at least this well, then everything is beautiful in repeated games and you get the same results as price of energy. I will give you one slide hint of how this gets proved. But in fact, given that this is not 10 years old, I want to actually spend my time on trying to go beyond this and tell you what one significant disadvantage of it. So just to give you one sense, maybe I'll have a slide repeating the sentence I already said a minute ago. So how do we measure welfare in a, it's like GDP. I added up everyone's happiness. So social welfare with an outcome A is the sum of all the people's utility at that outcome A. And what we would prefer if, social welfare at a Nash equilibrium, one would be the same as social welfare at the optimum. And to be honest, the equal sign at the very end shouldn't have been there. So A star is the best social welfare, A is some sort of Nash equilibrium. What happens that in the proofs, turns out we never use anything about Nash except this one inequality. That is, the one inequality is that no player I prefers his optimal strategy to what he's doing now. Nash is much stronger than that. They don't prefer all kinds of other things. But those tend not to be useful in the proofs. And if the proof has this property that this is the one inequality used, then it's very easy to extend it to no regret learning outcomes, because no regret really says this, except you have to hit it with a summation over time. It says exactly the same thing. And then you can extend the proof with a little bit of massaging, because, of course, no regret had the error term, which Nash didn't have. Anyway, this is all I wanted to tell you. What really happened here is that, this sequence of papers observed that in more and more games, literally that's the one inequality we use, and therefore it naturally extends. One handicap, and this is what's going to be sort of the new technical focus of what I want to tell you about, a critical assumption in all of these games is that when you do a new copy or new time period, then there is no carryover effect in between runs, that you start a clean copy of the game. And you ask, is this a reasonable assumption? And my general answer is a clear maybe. So depends what your time scale is. Going to car traffic, if I think of morning rush hour as my time scale, it's perfectly fine. No matter how bad traffic was Monday morning, by Tuesday morning, those cars are gone. Overnight, they went home. Something happened. But if I change the time scale either on cars or on packets, and I guess on my other slide it's a millisecond by millisecond packet traffic, then it's not true. The very same cars that were there a minute ago, they're still there. They're still causing congestion. So that's not a new copy. And I guess with cars, maybe as you're driving, the morning rush hour is a reasonable time scale because your repeats will be the next morning. But in packets, that's not a good time scale. Time scales, because here the learners are the routers, and the routers are working in this millisecond by millisecond time scale. So there it's not a good assumption. I guess the main thing that I'm going to tell you a little bit is that is a sequence of papers with my student Jason Gaitonde, whose picture you can admire here, in a very simplified version of packet routing. Instead of complicated networks, we just had queues and servers. And where the leftover effect was is literally what is happening on the internet. If a packets will try to go to the servers, but if the server doesn't serve them, then you're going to have to get resent. This is how the internet works. And that's a leftover effect. If you're not doing well in getting served, you have a lot of packets in your hand. You have to keep sending them. So that's going to be one example. Just to tell you that this is more common than just packet routing, another maybe even bigger killer application is budgeted auctions. Budgeted auctions are like the advertisement auctions where if you actually are an advertiser, the very first thing Google will ask you, how much is your monthly budget? How much money do you willing to spend this month on this business? And then they ask you other questions about your values. And the budget is the carryover effect. If you succeeded in winning, there's less money in your budget. If you failed at winning, well, then I guess there is a lot of money in your budget. There is a sequence of papers I'm highlighting here, and I think the slides will be up available, the last of which is with the student Georgios Fikiouris, whose picture you can see there. But I'm not going to talk about budgeted auctions in this talk. So the questions we like asking is the very same questions that you have seen or I mentioned in the beginning, but I guess with this extra question. No-regret learning seemed like an ideal thing under the assumption that the new copies are independent. Is it still good enough? Or do I have to think of something better? And of course, I'm going to ask the same sort of questions. How good is the outcome, or how much extra capacity do I have to give the system to guarantee a good outcome? Okay, so let me tell you a little bit about this particular one model, the queuing system. And again, it's a very simplified model of the internet. So queues, packets arrive, they're queues and they want to get their packet served. We're going to assume it's a probabilistic model. We assume that packets arrive at some rate at qi at some rate lambda I, and the servers are maybe not perfect, and each are serving at this probability mu j. To be honest, you can forget the mu j's, and servers can be perfect. That's in our model because induction works better this way. But sorry. The main part of the model, and that's a true fact about the internet, is that every queue can only send to one server at a time because they have one server head. Even if they have 7 packets behind them and there are many servers they could send to, they have to choose which one they send to because that's what they're capable of. And similarly, every server can only serve one packet at a time. And if there are many packets went that way, which was true on the previous slide, you have to serve one and have to drop the others. I'm going to make the assumption that unserved packets instantly get dropped, that is, went back to the server. To be realistic, each of them have a tiny buffer, and they would keep it in the buffer, but in our model, we forgot about the buffers. So that's certainly a simplification. One thing I'm going to help the systems get somewhere is that I make servers attempt to serve the oldest packet. This definitely helps. Like getting the oldest packet served helps you get stuff through, if at all possible. So this is our model. Again, queues are trying to get the packets to the servers. I'm going to assume that each queue running a learning algorithm. In reality, they're running something simplistic. but it seems good enough to actually learn. I have to start by giving you a quick reminder of basic queuing theory. So if there aren't like many queues and many servers and no learning needed, one queue, one server, then that's sort of classic 101 queuing theory. It says that if there's arrival rate lambda and service rate mu, then of course you need that lambda is less than mu, otherwise you can't get the packets through. And this is the only condition you need. If lambda is less than mu, you're okay. If greater than mu, obviously not okay. Packets come too fast, and equal mu is also actually not okay. That's the condition. Based on this, I hope you're going to believe me of what the condition is if I can coordinate. And there's a very natural condition here. To state that condition, it's natural for me to sort the queues and servers in decreasing order. This is just for notational convenience. And here is my condition. And I guess instead of reading it out, let me actually start with, so something true for all k, I'm going to start with k equals 1. So k equals 1, the condition says the queue that has the highest arrival rate, there better be a server that can serve him. Remember that queue can only send to one place. So if there isn't a one place that can serve him alone, you're definitely host. Forget the other queues. And similarly, two queues can send to two servers together. If there aren't a pair of servers that have enough capacity for the two of them, again, you're host. And this is true for every k. So every k queue, there should be k servers that have enough capacity to serve them, and enough here means a strict inequality for the same reason we had on the single server. So I hope this is a believable condition, not super hard to prove, that if you coordinate, this is what's doable. It's a matching style argument. So the question is, how much extra capacity do I have to give a system if I'm not coordinating? And they're going to collide with each other and get in trouble as they're learning. And here is the answer. If they're doing no-regret learning, you need to double the capacity. And in the next 2 slides, I'm going to try to convince you that no-regret is a reasonable assumption here, and indeed you really need the double if you do that. We did work this out in this very simplified system, but actually there is a beautiful extension from Hu, Fu, and Lin in the Vine 2022 proceedings that extends it for general networks. What's interesting is instead of looking at learning outcome, I go back to the old-fashioned version and think about, wait, how about Nash equilibrium? Then I don't need to beef it up by that much. You can do better, or you don't need quite as much. And what I'm going to end the talk with, after I show you a little bit of why the factor of 2 is really there, is what's wrong with no-regret learning? And I don't have the answer of what would be the right thing instead. I know what's wrong. I just don't know. I don't have a better solution at the moment. So let me give you a little hint of the first result here. The proof of the first result here, this one, is a very nice probabilistic argument, and maybe hopefully many of you will appreciate it. Let me try to give you a hint. It's based on a nice theorem of Pimentel and Rosenthal, which says that if you have a probabilistic process, so that a number that sometimes goes up and sometimes goes down, then under the following 2 conditions, you can prove that the expectation remains bounded. What are the 2 conditions? One is some sort of regularity, like second moments are bounded, I think, technically, or some other conditions are good there, but something like the second moments are bounded. But more interestingly, the second item here, that when the number is big, it has a negative drift. So when the number is small, then it's okay if it goes up. But there is some bound, like if it went above 1 million, then the expectation is coming down. And then in this high probability, the expectation will remain bounded at all times. I use that for a potential function that's effectively the following: sum of the ages of all the packets in the system, roughly speaking. So for every packet, I add up its age, and that sum is what the potential function is. And obviously, if the sum of ages will remain bounded, then of course every packet in particular didn't stay there too long. So it indeed shows this, and what I want to give you on the next slide is that no-regret condition, and the factor of 2 slacking capacities actually causes the negative drift. And for this talk, I'm going to ignore the sufficiently regular condition, which we need to work at. So again, the goal is to give you a sense of why the factor of 2 is needed and why is no regret a useful condition. And here is how the proof goes. I want to focus on old packets in the system. So say there is a cut of tau, and I look at all the packets that have tau old. And remember, because I favor old packets, this group as a whole has priority. So I guess I'm going to claim that there are 2 cases. Case 1, that the queues that had these old packets were smart enough to send them to the right servers, the one that has high capacity, or at least do so half of the time. Half of the time is good enough because the capacity is double, so half of the time should be enough to actually clear the packets, and then at least this part, the old packet set, will decrease, will vanish because they get served, and that would be good for us. If somehow they were too dumb and sent it someplace else, then I want to use the no regret condition. Wait, these old servers half of the time were empty, and you had priority. Why didn't you use them? You must have no regret over, you would have regret unless you got served someplace else, and therefore you still got enough service. And that's where the no regret comes in. That also gives you a sense of why I need the factor of 2 in here, because my band was either use it half of the time or it's empty half of the time. This needs a half of the time blow up here. And in fact, and I have to do this for every threshold, of course. And in fact, this band is tight, and it's not hard to come up with examples where no regret learning does badly. Remember, my claim is that if you're not dumb enough to just do no regret learning, then you could do better. And I will not prove this to you, but I want to show you an example that maybe gets across what's wrong with no regret learning. So that's the next thing that will happen, is an example. It's a very simple example. So let me remind you again what the model is. On these blue boxes are queues that have packets arriving. In this case, both of them have packets arriving at a little bit higher rate than 50%. And on the right-hand side, there are servers. One is a perfect server, and one is a bit worse than 50% in its capacity to serve. First of all, let's agree that there's plenty capacity here. Altogether, if you only coordinated, life would be good. Because if I coordinated, the rule was that the mu of 1 should be bigger than 0.51. Yeah, sure, it's a lot bigger. And also should be that the 2 of them together, which is 1.02, should be less than the sum of the server capacities, also true. We also can conclude that if we don't have the factor of 2 blow up that's needed for selfish behavior, and that's because, I guess it's not true anywhere. 51 is a bit more than twice 51 is a bit more than 1, and then the sum of them twice is even worse. In fact, what you see on the picture is the unique Nash equilibrium, unique no regret outcome. If they both send to the top servers, they're identical. They're going to share the service rate roughly 50-50. We have 50% service rate. They have no regret. The other server is worse. So they're happy. That is medium happy, because of course they're not getting their packets through. There's only a service rate of 1, and together they have an arrival rate of 1.02, so there will be slow linear growth, and there is nothing they can do about this. If any one of them were to deviate, then that guy, here the lower guy, of course will have regret. Wait, 10% of the time I'm sending to this mediocre server. Up there I had 50% success rate, he's only 47%. That's really bad. I have regret. Except it helps. And I mean selfishly. So a priori it looks like this is actually an altruistic move, because 10% of the time you came off of that server, you let the other guy get service on his own. That's really good for your body. 10% he's getting across. But it turns out it's good for you, because you let the other guy get across 10% of the time, quite often he's going to have no packets to send. So your service rate up there will be better than 50%. Often you're alone. So you have a lot of regret, but you're getting all your packets through. Whereas when you had no regret, then you didn't get your packets through. So something weird is happening here with no regret. So let me actually tell you what went wrong with no regret. And what went wrong, step number 1, was our notation was broken. Remember, I didn't used to have this upper index of 1 through t. I used to think that your outcome at time t depends only what you did at time t. That's not true in systems with carryover effect. Everything depends on the history. So I now changed my notation to say that, wait, what happens at time t to you, person I, is not only depending on what you all did at time t, it depends on what happened in the whole history, hence the funny notation. And it turns out that what no-regret algorithms do and what the no-regret condition does is what's actually known as explore-exploit. And any one of you who have seen no-regret algorithms, this is a catchword. Explore-exploit is what they do. What does explore-exploit mean? Is that you try these alternate strategies just for a second, and then you back off if it's no good. Try it for a second and back off if it's no good. In notation, that's what it does. You take the whole history, and one time you try X. And if you go back, this is what I told you about having regret. Upper, you have a service rate of above half in this case, and lower, you have only 0.47. So if you try the lower one, you regret it. It's 0.47 is not so good. But what I really meant in English was actually this notation, which maybe is too much to hope for. But when I said, what would happen if you always did X with hindsight? So that notation says that X might have a long-term benefit, and your algorithms, or at least my algorithms, to achieve the no regret are too myopic to notice long-term effects. And that's what we're getting wrong. So I guess when I said I know what's wrong, I just don't have a clear answer to, or have hints, but don't have a mathematical answer or better solutions, is that the way no-regret algorithms work, or the way the no-regret condition is written up, it's too myopic, and one's supposed to think about long-term effect. And I guess going back to the theorem I showed you a couple of slides back here in the bottom, unfortunately at the moment I don't have a learning algorithm can achieve this better band. I only know that Nash equilibrium achieves that better band. So that's an open question. And I guess I want to end with a couple of conclusions. So I guess I still think that no-regret learning, or generally learning, is an excellent way to play these repeated games. Again, games where the individual penalty for making a mistake is low, so and you repeat a lot, so you can learn from data. One better advantage that's not actually, was never on the slides, but definitely is one. No-regret learning adjusts to the opponent playing badly and beats him. That's a big advantage over playing Nash, where you assume that the other guy also is smart than playing Nash. Who knows? So definitely one advantage. If everyone does no-regret learning, or at least actually most results, if the majority of the players do it, then they're reasonable social welfare, even in many games with carryover effect. But I think there is room here to do better. And in some way, no regret in at least the games with carryover effect is a bit too myopic. And I think there is reasonable hope that one can prove better things with less myopic versions of even the similar condition. But that's the natural question that I'm going to end with. Is there an analog of no regret that's natural? If you look at data, people tend to satisfy it. And you can do better. It does better for social welfare than no regret. I'm sort of proposing that a more patient version that is literally fixing the problem we have seen. And when you try something, try it with more patience, might have this property. And I'm going to end here, and thank you very much.